I yes, now it's recording. Cool. Then the total, or you can say the left theory, is nothing but from this statistics that what's that skew and HQQ plot and KD box cost transformation we have. The main formulas that we have from here, this most important formulas we have in Chebyshev inequality. What's the bootstrapping is, then CI, and the last but not least, the finding the relationship between two, you can say, random variables or two distributions of features. That case, taste, covariance, and PCC, ISRCC, like that. So definitely, this is going to take one day. If we just as a like simple view, or we just visit once, but there would be like more doubts in it. So I am hoping like by tomorrow we would be finishing all this theory stuff, and rest all of the days. Good 4 days maybe. Wednesday, Thursday, Friday, and Saturday. 4 days we would be solving only the examples, and as and when required we will touch upon theory, basically the formulas, right? And how to address the, you can say, given example, where to apply that conditional probability, where to apply this that simple probability, right? Okay, and how to think like if the problem is of conditional probability or not, correct? Okay, so without wasting much time, I just took 1 more minute, but let's start the session now. So just to give you the glimpse of yesterday, we just saw what the probability is, what that mean, median, that median, and MAD, median absolute deviation is. Then we saw what the probability is, that approach how the naive or the classical formula probability works, right? If all the events have the equally likely, then and only you can use this formula. Okay, then we saw some axioms of probability, a mutually exclusive event, independent event, and now we are at the stage that we were discussing this random variable, or basically this histogram, PDF, and PMF, right? So what, and there is a very much difference between PMF and PDF. I was just reading that only before starting the session. I guess I have closed all the tabs. But what's the main difference between PMF and PDF, and what a y-axis set? Okay, so let's start with the random variable. So as we discussed to yesterday, random variable is nothing but kind of a spatial variable in a probability. In a linear algebra, we can have a variable to assign some value, right? Let's assume x is a height. Let's assume x is the profit. Let's assume x is the number of shares, like that. But in a probability we can also have the variable, and it is called random because our experiment is random itself, right? So it can take any random value. That's why we are saying it's a random variable, right? So it is nothing but saying all the, you can say, observations that you have for given event, given set, or anything, correct? Sample space basically. So the random variable is nothing mapping from an event to R. Okay, that's the boring definition. Okay, so the random variable can be anything. I can say let x equal to getting 4 or less. In basically, obviously, the experiment is dice throw, right? Or x can be amount of chocolate eaten by students, right? If there is a survey like what is the correlation between amount of chocolate eaten by students and the marks they got, like that. Correct. And this survey was done for the amount of chocolate per capita eaten versus the that Nobel Prize, number of Nobel Prize, average Nobel Prize got for a country. There we discuss like what's the difference between correlation and causation, right? Or X can be a time spent on website. But if you observe clear here, the first X or the first random variable or your first event, kind of this experiment, is discrete. Your dice throw can either have 1, 2, 3, 4, 5, 6. I can count like, so it's nothing but the discrete value it can take. But let's say my random variable is this: time spent on a website, time spent of website per user, the the user, like the time which is spent by user, a user on the website, on the, you can say, random, you can say, login. So this time can be anything: 1 minute, or 1 minute, 1 second, 1 second, 1 millisecond, 100 millisecond, 101 millisecond. So basically it can take all the values belongs to R, right? Not zero. or minus 0, right? So it's nothing but the continuous random variable, and this thing that you can count like all the outcome of the variable or the value that your random variable can take. It is nothing but the discrete random variable, correct? And if you have the discrete random variable, then all your outcomes, then if you want, then you can have the PMF. And what PMF is and what PDF is, so let's discuss now, right? So to understand the PMF and PDF first, we need to first understand the histogram, right? Histogram is nothing but the counting, simple counting, right? If you're writing the count 1 equal to 2, 2 equal to 1, 3 equal to 1, 4 equal to 2, 5 equal to 1, 6 equal to 1, like that, it's histogram. But we are just putting in this bar format, and there is one specialized. If it is that simple, then there is no meaning of using histogram, but we have something called bin, right? There were kind of an example, then the bin range was given, and then we need to calculate like how many numbers would be there in the given bin, 3 to 4, 4.5, or 4.5 to 6. So what is bin, what is histogram, let's understand. So given data here, just see, I have like explicitly, you can say, chosen this kind of an example where this x can be same values can be, you can say, the discrete also, or continuous also. Why? So if I say this x is representing number of pizzas sold in a day, right? Let's say I'm running a shop and I'm selling a pizza, says this is the number of pizza that is sold in a day, right? And I'm taking the observation from first of you can say March to 1 2 3 4 5 6 8 of March, like that. Then this is discrete variable because the number of pizzas sold on a day would be either one, either two, either three, like that, right? And see, I have upper limit, that's nothing but the my limitation of a shop. You can argue that it could be 1 2 3 4 5 6 up to infinity. No, it has a upper bound that from 1 to 50. If 50 visa is solved, I will close the shop, right? So let's take this assumption. So this can be discrete also, or this can be continuous also. To like explain the PDF and PMF side by side, that's why I will take the same x or same example to understand all these concepts, right? Okay, so let's take the histogram first. So for the given value of x 1, what is the frequency? Histogram is nothing but counting the frequency. For 1, it is 2. 2, I have one instance, right? For 4, it is 2, like that. For 1 and 4, it is 2, otherwise, it is 1. So, how can we saw it on the histogram, right? I cannot simply write 1, 2, 3, 4, 5, 6 and draw a bar chart. No. Histogram is used like draw, is like we can draw the histogram using the bin range. So what is the bin? So bin is nothing but this thing. The one you can say this rectangle is nothing but the bin, right? And bin range is nothing but the width of a brain bin, not a brain bin, right? And how can you take the width of a brain, width of a bin? Sorry, it's tongue twister for me. That you can decide using the number of bins, right? How you can say my that. That small bin you want to take, or how much information you want to take for the given range, it is decided by number of bins. So let's see, if I take number of bins equal to 4, then what will happen? So what is the maximum number? It is 6. What is the minimum number? It's 1. So max minus min divided by number of bins is nothing but the bin range, right? So 6 minus 1 divided by 4, it's nothing but 1.5. And why we are using this formula? So if I start at 1 and I need to end at 6, right? This is minimum, this is maximum, and I need to have the four you can say steps. One, two, first step, second step, third step, and fourth step I should reach 6. So like what should be the step size? That is decided by this formula, max minus min divided by number of bins. So 6 minus 1 5 divided by 4 is 1.5. So 1 to 1.5 plus 1.5 3 plus 1.5 4.5 plus 1.5 6. And so that's why I have 4 bins. Don't count this one. 1, 2, 3, 4, 5. No, it is not. Bin is nothing but this rectangle looking like area. So this is 1, 2, 3, 4. So if you count the numbers, it is 5. Any questions? I guess
Uh,
someone is trying to say
yeah,
something.
Mayur, like, how did you get number of bins for? Like, it's a user-defined value or?
No, we can take any value.
Okay.
It will decide like how you can say accurate you want to capture the data, or how like a small or bigger range you want to capture the data.
Based on the data and the size we have to take. Okay.
Hmm.
Yeah. Sure.
Yes.
Thank you.
I have not opened that thing here. I'll
This
go here.
bin thing is also a parameter of the function histogram, if I'm not wrong.
I
We
guess
can
yes. Bin.
explicitly,
How many bin you want?
yeah,
It you need to give. Histogram bin size.
We have plotting, right? Plotting with the number of bins we have.
Haha, I'm just trying to show you like how the bin size
Right.
will affect. Uh, Good example. Where is the good example? See, here it is. Correct. So if you are taking something like this, that for see here, bin width is $100, right? And gross monthly salary versus frequency. So see here, if you take bandwidth equal to $100, then you are calculating like how many employees, right? I'm not sure which data it is, but I guess it is a gross monthly salary, so it is number of employees, if I'm not wrong. So 800 to 900, you have 350 employees like that, right? So you have the step size of 100, right? So you are taking one, two, three, four, five, six, and 7 bins only. So if you reduce by 50, you are capturing more data. See, from this, like roughly your distribution is something like this. But using 50, it is looking something like this. 800 to 850, I have just 100 employees. In 850 to 900, I have around 250, right? So if you still decrease the bin width to $25, not bin width, bin width. So you are increasing bin, right? So now I have like more than 15 or 20 bins. Here I had just 8 bins. Again, if you just go further, it would be more and more data you will capture over the
So,
range.
so basically, we are taking more and more samples, right? You can say like that.
Definitely. Yes. Here we are not taking the sample out of population, but you can say we are like generalizing more, or we are going into more details. Here I was just calculating the number of employees between 800 to 900. But if you look here, I am calculating between 800 to 810, 10 to 20, 20 to 30, 30 to 40, like that, right? So at $10 range, I'm counting how many employees are there, right? So this will give you
bin
the
bin
really good, you can say, distribution of a salary across range, right? So if you take the like more bins, it will represent the exact distribution of the salary, right? So from this, you will make assumption that 800 to 10, 1000, it is same, then it is decreasing. No, but it is not something like that. It is something like this log distribution, right? Okay, guys. Any more questions? So as you increase the number of bins, the bin width will decrease. Makes sense, right? Uh, because the range is fixed, right? 800 to 1500. So if you increase the number of bins, the bin width will decrease, and you will capture the more and more data for smaller and smaller
inversely
range.
proportional.
Inversely proportional, basically. Yes. So let's take a small example for us. And if I had taken you can say more bins, then it would be see, and how to plot this. Okay. And there is a one you can say thing that is easy to make mistake is while calculating 1 to 1.5. Let's say I have 1.5. So should I count between this range or this range? 1 to 1.5, should I count 1.5 in the left range or the right range? So the answer is for the all the bins except last one, we need to count in the next one, right? So if you are going from 1 to 1.5, 1.5 is not included, right? 1.5 included in next bin. 1.5 to 3, so 3 is not included there. See, it is less than sign. Sorry for the mess up, but let's concentrate on this third one. So 3 to 4.5. 4.5 is not included, but for the last bin, the 6 is included, right? Otherwise, where the 6 will go? Correct? So there is a small thing that you need to remember here. Due to this, I was not getting exact histogram as numpy. I tried to implement the histogram from scratch, basically using the that bar plot. Right. So this was something that I learned while doing that experiment. Okay. So this is now easy. 1 to 1.5. You just need to see like how many observations I have. I have just two. So the height of the bin here would be 2. 1.5 to 3, I have one observation. 3.3 to 4.5, I have three observation. Right? 4.5 to 6, I have two observation, like that. Correct? And so this is the count 2, 1, 3, 2. So total count is nothing but 8. 1, 2, 3, 4, 5, 6, 7, 8. And this is nothing but the probability, right? So this if you divide the values, the histogram value, the count, if you what you are getting, and if you divide by total number of counts, that's nothing but the probability, right? So the probability of getting the value from 1 to 1.5 is 2 by 8, right? Because I have to two like observation of 1, two observation of 1 and 1, so 2 out of 8. So the probability of getting 1.5 to 3 is nothing but 1 by 8, and 3 to 4.5 is 3 by 8. And how it is? Because I have the observation of 3, like one observation of 3 and two observation of 4, right? So the total probability, if you count 1 by 8, 2 by 8, is nothing but 3 by 8, right? So if you divide all the counts by probability, 2 by 8, 1 by 8, you will get the PMF, right? This is nothing but the PMF. And this is not true, you can say. This is like looking like a true. This is you can say this makes sense, but this is not the actual probability that we have on the PDF. That's very, you can say, complicated to understand it. But say we here we have this discrete data, so that's why the probability this on PMF y-axis will always give you the, you can say, probability. So how PMF is made? PMF is made using the probability for given you can say value 1, 2, 3, 4, 5, 6. Right. So this is nothing but the PMF. For one, probability is 2 by 8, 2, 3, 1 by 8, 4, 2 by 8, 5, 1 by 8, 1 by 8, like this. Right. And the PDF is always used for the continuous random variable. So if this data was for a diameter of mango in inch, right? Then I will have this you can say PDF. And how do you get it? So see, and how to you can say interpret the PDF. So PDF, the full form of PDF is nothing but probability density function, right? So we don't have you can say probability here. It's not, it's a density, right? So the more you can say more likelihood, like you will get you can say diameter of mango in 1 inch. It's very dense here, right? That's why it has high value. So there are very high chances that you will get the diameter of mango in 2 inches, or same way for 4 inches, like that. You can't say this is the probability, right? You can't
Can
you can say
we derive probability from PDF by any formula or something?
it's actually, if you want to derive the probability out of PDF, you need to take a range, small range, 1 to 0.001 dx, basically, and take what is the
Yeah, we have to
area there.
integrate.
Huh, take the
Okay.
area, yes. And see, actually, how this makes sense is, I don't know if that got open. Let me take paint. um, if you remember that continuous distribution, not continuous uniform distribution, right? Discrete uniform distribution, then it is looking something like this. If it is starting from A to B, and it is, let's say, continuous discrete way, continuous uniform distribution, right? Continuous uniform distribution, then this height is nothing but 1 divided by B minus A, right? If the this distribution is from range A to B, right? Why? Because this area, The area I'm talking about is this. Should be 1 only. So how this area would be 1? I need to multiply b minus a multiplied by 1 divided by b minus a. Then and only it would be 1. That's why if it is ranging from a to b, the height on PDF, right? I am talking about a continuous uniform distribution. Then the height in the PDF would be 1 divided by b minus a. Now let me take a equal to 1 and b equal to, let's say, 1.5. Then what would be the height? Height would be 2. Can you say the probability is 2 for a? For continuous uniform distribution, the probability of all point between a and b is similar, and it is equal to 1 divided by b minus a. So, right? So the probability is similar, but this is not a probability. This is probability density, right? So this value is 2. So you can't say this is probability for a given point. Let's say 1.4. The probability is not 2. It will go worse if I take 1.1. Then this value would be nothing but 1 divided by 0.110. Can you say probability? Is no, it is density. So from PDF you can't say the this thing. This is the probability. It's density, probability density, right? Now, what about PMF? So if I take the same example, but now I have continuous discrete distribution, right? Continuous, but it is discrete. Then it will look something like this: one, two, three, four, right? I have the same probability over A and B, and this is nothing but the this thing, the probability here. In PMF, it is probability mass function. So if you think intuitively, this is mass and this is density. P in PDF, this is density, right? And what would be the size of this? Anyone? B minus A divided by number of observation I have. Right, so if it is ranging from, let's say, 2 to 2, then 3, then 4, 5, 6, 7. So the probability of all these observation would be 1, 2, 3, 4, 5, 6, 1 by 6, 1 by 6, 1 by 6, like that. So the great, you can say, example would be throwing a dice. Then I have 1, 2, 3, 4, 5, 6, and all the value is nothing but 6. Sorry, is this formula wrong or what? 1 by n, no? 1 by n. 1 by n, sorry, not b minus a by n, 1 by n. Number of observation I have, 1 divided by n. Correct? So if I have 6 observation, the probability of each would be 1 by 6, 1 by 6, 1 by 6. So they all sum up to 1. Correct? Let's get back to our business, PMF and PDF. I guess now it's clear, right? And this PDF is derived from this histogram basically. So once you have this histogram, you use something called KDE, kernel density estimation estimator, and you try to smooth, you can say, get the smooth curve out of this discrete, you can say, graph, this discrete distribution, and because it is not possible to get the continuous data. Can you get the data for all the heights possible, all the infinite heights? So you'll have the data for 160, 161, 162, maybe 162.5. So you'll get always this discrete data, but out of the discrete data, you are trying to make the guess for the continuous, you can say, variable, right? So if the probability, if you know the probability of 160 and 160.5, so you can try to estimate for what is the probability for 160.4, if you don't have if you don't have that observation. So out of this discrete data, we try to make some assumption, right? Like this, using KDE, we try to make the assumption like this, right? Now it is continuous. Now I know what's the value at 800.1. Correct? And if I make assumption here, it will look something like this. So more the minute information you have at the micro level, the more accurate the result you will get, right? Okay, so out of histogram, this PDF is made, because here, if you think intuitively, I'm just counting all like where all mass is, right? Where everything is, you can say densed, right? So I have more density at 3 and 4.5 there, therefore I have less, so sorry, the more the height of the bean is, like that. Okay, now let's have some you can say formula. So how we can terminology basically. So PDF is defined as f of x, and PMF is mostly defined as p. And we should follow this kind of a thing. I was just reading on Medium that on y-axis if it's the PDF, just use the f. So we know like this is the probability density function, and if it's PMF, use p because it is actual probability 1 by n, right? In case of continuous, basically, correct. And here in PMF, I just wrote that p of x is nothing but p of x. The probability mass function capital P of x is the probability itself, right? The CDF, what CDF is? CDF is really beautiful. Sometimes you can make a really good you can say judgment, or and actually we use CDF in error also, in logic, in that model, machine learning model. If you got all the errors out of all the observations given training data, whatever the error you have made for given all you can say value of x, let's you get EI. Now if you want to see like how your model is doing, then the CDF is really useful, right? So let's see like what CDF is. Everyone should have remember it's nothing but the summation of all the probability up to x, right? X is less than a, that means up to x, a value, x value of a, right? Up to a range. In case of PMF, it is summation, and in case of PDF, it is nothing but the integration, right? For the continuous value, you cannot sum all the infinite value. So you are taking the dx step and you are integrating over the range. Okay, so let's try to figure out the this CDF first in table, then we will try to plot it. So for x equal to a, I have 1, 2, 3, 4, 5, 6. So this is nothing but the total, what you can say, unique values I have out of this set. Now let me see what's the probability. Or no, first let's count it. So out of count, I can find the probability. So the count of 1 is 2, then 3, 4, like this, right? Why I have written like this? Okay, this is nothing but the you can say cumulative count, right? So x less than a, what is the meaning of x less than a? So if I take x equal to 1, if I take x equal to 1, how many number of observation I have such that the value of x is less or equal to 1? So I have two counts, right? 1 and 2. So I've written 2. That's fine, Suresh. Okay, so what's how many counts do I have less than or equal to 2? So 1, 1 and 2. So I have 3 counts. I hope you get the idea, right? So if I need to calculate for 4, I have 1, 2, 3, 4, 5, 6 counts. And if I go up to 6, I get all the counts. That's nothing but 8. Now, this is nothing but the probability I have written 2 by 8, 1 by 8, 1 by 2 by 8. The probability of each number for a, x equal to a. Now, if I want to find out the CDF, it is nothing but capital F, and CDF cumulative, it is cumulative in nature. That's why we have x less than a, always like this. PDF is like PDF or PMF is at particular point. What is the density or what is the probability? So x equal to a, it's nothing but PDF or PMF. Less than or equal to a, that means I am counting all the probabilities. What is the probability of getting x less than a, right? So this is the cumulative probability, you can say 2 by 8, 3 by 8. So this is cumulative count, right? So cumulative count divided by total number of count is nothing but the cumulative probability. 2 by 8, 3 by 8, 4 by 8, 8 by 8. So what is the meaning of 8 by 8? It's nothing but 1. So what is the chance that you will observe the 6-inch diameter of a mango or less than that? It's 100%, right? Because all the values are either 6 or less than 6, right? So it's 1. That's how like I have this you can say CDF values, and now I can plot it, right? So I will take 1, 2, 3, 4, 5, 6, and I will plot it. So 1 to 2, I have to go 2 by 8. Then again after 1, right? Because it is less than or equal to 1, right? So there is also one common you can say confusion even I had, that where to stop, like where to give this step. at exit 2 or at exit 1. I have this value, right? 2 by 8 and 3 by 8. So how much should be the width? So it's up to 1, right? Because x is less than or equal to a. So after 1, it is nothing but 3 by 8 up to 2. Now 2 to 3, I have 4 by 8, and then 6 by 8, then 7 by 8, 8 by 8, like that. And if it is was case was, you can say, mango size, not a pizza, then it would look something like this: continuous CDF, right? So if you have PMF, you will get this step kind of a CDF. It is called, there is one proper name given to this kind of a graph. I am not getting it top of my head. And if you have this, you can say, PDF or continuous random variable, then you will get some CDF looking something like this, right? In case of mango size, because it can be anything, 1.5, 1.56 inch, like that. Any doubt, guys, till now? PDF, CDF, and PMF, even histogram?
Mayur, how do
Yes.
we calculate CDF from PDF actually, and vice versa?
Okay, actually, thanks. Actually, I just forgot to mention. Uh, Sorry. Okay,
No,
so,
nothing, nothing.
huh, so how to get the CDF out of PDF? So if you think CDF is nothing but the cumulative probability, right? Or it is cumulative density function. It is called, right? CDF,
Yes,
cumulative
yes.
distribution function or density function?
Distribution, I guess.
Distribution, no? Cumulative distribution. Yes. Let's be clear then in doubt. CDF full form. It will give me everything. Cumulative distribution function. Okay. So how to get CDF out of PDF is, so let's take one example. Then I will give you the intuition behind the PDF to CDF. Out of PMF, getting the CDF is really easy. Okay, I don't need to draw it. I have here. I have it here. Huh. Let's take not this example. Do I have good one? That 1 by 6, 1 by 6. Huh. This looks correct, but I need one more. Okay, that's fine. So if I throw a dice, so what is the probability of 1, 2, 3, 4, 5, 6? It is same, right? Over the place, 3, 4, 5, right? For 1, 2, 3, 4, 5, 6, it is 1 by 6. So how to get the CDF out of it? So first, 0 to 1, what is the probability? Total probability I have, it is 1 by 6. I have just changed the scale. Now up to 2, what is the probability? So it's 1 by 6 plus 1 by 6. So it's 2 by 6. 1 would be here, 2 would be here. So getting the value out of dice less or equal to 2 is 2 by 6. Either you will get 1, either you will get 2. So 1 and 2 combine, it's 2 by 6. Then it will then jump on to 3 by 6, then 4 by 6, then 5 by 6, and at last it would be 1. Right? At last it would be 1. And always the last value is always 100%. Right? So this was nothing but about discrete. What about continuous? Right, so if I have continuous distribution, then what happen is, so if I have some PDF looking something like this, let's say, all count to 0, so let's have something like this, right? So how can I get the CDF? So what I'll do, so the CDF at any point is nothing but the integration up to that point, right? So to get the CDF at this point, x equal to a, at this point x equal to a, right? So this CDF value shows like what is the probability of x getting less or equal to a, right? So how can I get that? So first I will take some small area, put it here. Then I will take more small area. So this area is sum up to here. Then I will take one more area, then it will sum up to here. So basically what I'm doing is I'm taking integration over 0 to a for given PDF value f of x. So this is nothing but my CDF. or you can say capital F of x less than or equal to a. I guess now the idea is clear, right? So CDF is nothing but the integration of PDF over the range, and vice versa. If you want to go from CDF to PDF, you just need to take the differentiation. That's all.
Yeah, yeah, got it, Maya.
Correct?
Yeah. One
For
more doubt.
uh,
Yeah. Uh,
no, nothing, nothing.
a PDF of y-axis will not be equal to 1, right? It can be any scale, right? Only
Okay, why
CDF it
I
will be
wrote
1.
PDM? It is PDF. For PDF, the value of y can be even 1,000 also.
Yeah, that what. Okay.
I can
Only
get
for
like simple example and it would be 1,000. Correct?
yes, yes.
Okay. Mm, great. Let me come on to this.
Mayur,
Yes.
Mayur, what is there on the y-axis for PDF and PN?
For
I mean,
PMF, it is probability. For PDF, it is not a probability, but it's a density. And for PDF,
density means count. You're saying?
you can say in a way, but see in PDF, see what's the difference between then histogram and PDF, right? In histogram,
Hmm.
you don't need to like the sum, the area of the sum, all the area. If it's just the sum of the area should not be equal to one. But in case of PDF, so you can think intuitively something like this. You just take all the count and divide by such a number. Divide by such a number. It's not always true. I am just giving you kind of an intuition that all the area, if you count all the area, it should be equal to 1, right? So it is nothing
Okay.
but density. So if you take all the density of given substance, then it's nothing but equal to mass, right? Total mass. And the total mass in case here, it is nothing but the probability. So the total probability should be 1. Correct?
Mm-hmm.
So this is
Okay.
kind of like how the density is distributed over all the values, right? So someone was giving example like this. I'm just drawing on a diagram. It was not they were trying to make intuition between the meaning of density in physics and maths, right? So if you have something like this, some substance like this, it is possible that it is thick here, right? More density is here, then less density here. It is more dense like this, and here it is like very less density, right? So this is nothing but the distribution of density across different area or value in case of random variable. So if you sum up all the density, then it's nothing but the mass, the total mass of this object, right? Similarly in PDF, this is nothing but the density over all the area, right? And you can't have you can say density for just one point. At one point it is not possible. You just need to take the small part out of it. It can be tends to 0, nearly equal to 0, tends to 0, the dx can be. But dx is nothing but dx is not never 0. In limit we said dx tends to 0, but it is just kind of a mathematical hack, and they try to prove it like that. Correct?
Mm-hmm. Okay.
It's really like I just read like one or two articles, but everyone is like a different. You can say kind of understanding for PDF. Even Math Stack Exchange I try, Simple Stack Exchange, and Medium.
Yes, my one fellow will tell one way, another fellow will
Haha,
tell another.
correct,
That
correct.
is
It's
what
it's
confused.
yes, it's never like easy to understand this PDF,
Yeah.
but we should have this kind of interpretation that around 4 there is more density. That means the chances of getting value around 4 is high. How many
Right.
chances? Just go and calculate probability. Don't tell like this is the probability from PDF. This is density. It is saying what how much dense the probability is around 4, and it is high. We can say that, right? Around 3 and 4, I am getting more value.
Okay. So this cannot be more than one, na, then, Mayur? PDF.
See this thing. This density can be 100
Huh?
also.
Overall, it can be one combined.
The area should be one, right? The area should be one. So if I take something like this 1 and 1.1, I have let's say I can have any number of values here. infinite number of values I can have, right? So this is
Correct.
continuous
On the
distribution.
y-axis.
On the
Hmm.
y-axis, it would be the area would be 10. Sorry, not area. This height would be 10. For continuous distribution, this would be 10, right? So if you multiply it by 10 multiplied by 1.1 minus 0 minus 1 is zero point 0.1. Sorry, multiply by zero point 0.1, it would be 1,
Hmm.
right?
Got it. Got
So
it.
this
Got
is
it.
saying the density, and the density around all the point is similar. That means this is
Now I got it.
uniform distribution,
Hmm.
like this. Si- Purely like made on a lathe or milling machine. Okay. What's the expectation then? So the expectation is nothing but you can say what's the expected value of X then? Right now I am saying what's the expected value of pizza that I will sell on a day. If this is the 8 value I have from 1st March to 8 March, and I want to decide like how much material should I take on the 9th March, then what's the expectation? The simple approach would be nothing but not using any forecasting method or deep learning method. I will just take the average, right? So it's nothing but expectation, right? So the expectation and in this probability, guys, the great I must say, like I don't know why they have made this much difficult, but they have defined expectation of x like this: sigma over x. So all the value of x, that is nothing but all the value of observation, right? Understand this formula, because when we are going to solve the problems, if you have the intuitive understanding of the formula, then and only you can understand like what kind of problem it is and what kind of approach should I take, right? So sigma x px, so what is the meaning of this? X is nothing but all my observations that I have, all the values that it can take, the random variable can take, multiplied by the probability of being the value of x equal to x, like that. And so this is the value and this is the probability of getting that value, right? So if we talk about over this pizza or mango example, this is pizza example because I'm taking the summation. In case of that mangoes, or you can say the continuous variable, it would be integration, right? So x into px, so x is 1. What is the probability of 1? 2 by 8, right? From this table we know like what is the probability of 1? 2 by 8. The next value it can take is 2. What is the probability? 1 by 8. So 1 into 2 by 8, 2 into 1 by 8, 3 into 1 by 8, so on and so forth. Now you will get, and this px is PMF, PMF function, PMF, as you have guessed, in case of discrete random variable, and in case of continuous random variable, it is PDF, right? So it would be x into fx, correct? But to create more confusion, I don't know, everyone is writing xpx for PDF also. Okay, x fx dx. In some you can say formulas or the numericals, I saw xpx they are writing, but the understanding should be there. Like what should I write here? PDF here, right? Okay, so if the math, if we get the math workout, we get value of 3.25. So 3.25 is my expected value of x, right? Next day, what would be the number of pizza that I would be selling? It's nothing but the average of 1 to 8. Or if you can simple average, get the simple average 1 plus 1 plus 2 plus 3 plus 4 4 4 like divided by 8, you will get the same value, right? So for it is really kind of the same. You can the similar value in case of PDF, right? Because the probability is nothing but the count divided by total number of count. So if you do this x into px, definitely you're going to get this kind of answer 3.25, or you can say the mean value basically, right? So sometimes it is written as mu also, and basically it is mean basically, right? So what is the average value of x that you can expect? That's why it is called expectation, or you can say expected value of x. Okay, in case of continuous variable, what you will do, you will just take all the value of x it can take. Definitely you cannot write something like this 1.001. You need to like perform the all the magics, all the formulas of the integration, and try to figure out what the value is, right? Otherwise, why there is two formula, right? Because you need to apply integration x square by dx if you have x equal to x, something like that, correct? And then try to find out what is the area. or you can say what is the expectation in this case.
So,
Okay.
Mayur, what would be the range of the integration in this case? You have just written X, and in case of PDF, like there could be numerical, like continuous values.
Hmm.
So, how would we do the integration? Like after integration, what would be the range
It
in
can be
PMF?
anything, no.
So,
It can be anything because this value of x can be anything, no. So what we are doing, see, these two formula is literally the same, but why we are doing integration is because this x can vary from given range. So if you remember, there was one you can say problem, like what would be the expected value of a sorter stick if you break your stick in half, right? Shorter stick, right? So it can vary from 0 to zero point 0.5 if it is 1 meter long. So it can 0.001. What you will do in that case, right? So you will take the integration. So if I'm talking about let's say 0 to 1,000 meter long pipe, then the expected value would be 500, right? Let's assume that's the answer. In case of 0 to 1, it would be zero point 0.5. So there is no, you can say, kind of a particular limit to get the value of expectation, right?
okay, thanks.
Uh, was that the
Now,
question or? Huh?
my one doubt. You told 0 to 1 is point 0.5, right? How it got it?
No, no. I'm just saying that there was like one question. If we break the stick into half, uh, if we break the stick into half, what is the expected value of sorter stick, right? So let's
Okay,
say
okay.
they say like this stick is 1 meter long, right? The answer is not point 0.5. I was just saying, right? But let's say the stick is 1,000 meter, 1 kilometer long, like that, just hypothetically, right? So whatever
Okay.
the answer you are getting, let's say you are getting the answer 0.25 here it would be 250, like this. So there is no range, the value of expectation of x could be. And the range in this integration, I guess that was the question that I missed completely. It is nothing but the range in between, you want to calculate this expectation of x, right? So from this range, the x can take value from this range 0 to let's say zero point 0.5. The shorter stick can be 0 to zero point 0.5, right? It cannot be greater than zero point 0.5, so the range would be 0 to zero point 0.5 in this case, right? And out of 0 to zero point 0.5, what is the expected value of x? Now that we need to calculate. If I am allowed to like break the stick into just this particular discrete part, I can just take the part of point 0.1, point 0.2, point 0.3, like that. Then I won't take integration, I will take the summation, right? What is the probability of getting point 0.1, sorry, point 0.1 multiplied by what is the probability plus point 0.2, what is the probability, like that. But in this case, I can break the stick into at any point, right? I can break it here, I can break it here, I can break it here. That's why we are taking the integration. In this case also, the range of x was nothing but 0 to this thing, zero point 0.5, but it was in step size of zero point 0.1, right? So here the x was belonging to 0, 0.1, 0.2, like this. But here it is continuous. That's why we are taking this integration. And the range is nothing but the minimum value x can take and the maximum value x can take.
That
I,
means it depends on total depends on data. But if it
ah,
has like various too much distributed data in small range, then you can take integration. And if you have
I can't get your question, but
no, not question. I'm just confirming yours what you're saying.
uh-huh,
Like if you have 0 to 1, and if you have larger bins, like in histogram you have
uh-huh.
bigger bins, then you have to just
Correct. So we are
integration.
basically averaging out this area.
Yes.
If you think intuitively, we are just averaging out the area, right?
Yes.
Okay. And it makes sense, right? If we take x multiplied by probability of x, like this, and this is nothing but the density of a probability, right? So that's how this it's defined. So we are just averaging out the density, and it will give you the expectation of x, like that. Okay, so let's talk about the variance. I guess there is one more formula. I don't know why I have missed that. Okay, so variance of x is nothing but expectation of x square minus mu square. There is a proof given in the lecture content, and it's straightforward. I don't remember it top of my head, but you can see that if you have still doubt, like how we come up with this formula. So variance of x is defined as variance of, you can say, random variable x is expectation of x square minus mu square, right? And if I want to write this equation in one more form, which is sometime useful, I can write this as expectation of x square as it is, uh, right? Minus, what is the mu? Mu is nothing but mean expectation of x, right? And this is, I am taking the whole square, right? Mu square is nothing but expectation of x. Mu is, so ex square, right? So sometimes variance is also written something like this, right? Variance of x sigma square, correct? So I guess the formulas, each formula in the this probability intro is done. Now the next step would be this distributions. Before that, any doubt, guys, or any general question or anything before going to distribution? And if it is possible, I will try to finish all the distribution by today. So earlier we can start this thing, numericals, right? So by tomorrow, this statistics, the thing we will finish, and from Wednesday we'll start numericals because there are plenty. Okay, guys. So, any questions? Just give me a second. Let me have some water. Not. Hmm. Okay. So, distributions in probability. First, we will start with the Bernoulli distribution. And first, of course, why distribution is needed is nothing but it's, you can say, the old way, 18th century, you can say, or before that, 18th, 19th century way of machine learning, I will say, basically. That's why this probabilistic guys always say machine learning is probability only. Why? Because what they were doing is, given all the experiment, or you can say all the event in universe, they were finding a pattern, right? Some kind of a pattern. If you recall that Weibull distribution, so Weibull distribution is nothing but the pattern observed in nature for the extreme events, right? Extreme events means that Cherrapunji, in Cherrapunji you had drought, or the average rain was just 5 centimeter, like that. So it's extreme condition, right? Or in Rajasthan you get kind of a flood, right? So this extreme event, the distribution of extreme event over 100 years, they can collect the data and try to formulate it, right? So what is the probability of getting this extreme event or some common event, right? So during this bombarding in first or second world war, I believe, they found a pattern that the, like, at the time interval they will bomb, they were like have that jet planes and bombard, like throwing a bomb. That frequency was following a Poisson distribution, poison or Poisson distribution, that Poisson distribution, right? So what they are doing is they are observing it, they are trying to make a graph, like what is the probability of getting this time interval, the time between the first bomb and next bomb, given like it is a, the bomb, like it was a bomb, like they say, they throw a bomb at 2 p.m., then what is the probability that I will get the next, you can say, jet plane by 3 p.m. So all that they basically formulate it. So all this formula is derived. How cool it is, right? By just by just observing this kind of distribution over a time, the event which is occurring at a particular event, and it is not a like exit at 2 p.m., at 3 p.m., 4 p.m., right? So all this interval, or at this interval the event is occurring. So given all this data, if you can formulate it like this, it's really beautiful, right? The first one that got this kind of a formula. that currently we are not able to even memorize, right? So how they got this kind of a beautiful like formula for this kind of a graph, right? That this distribution they formulate it, right? So that's all idea, or you can say story behind the distribution, why it's useful, right? And every distribution has kind of you can say applications, right? Okay, so having said that, let's start with the simplest you can say the formulation of a you can say simplest event possible in the world of probability, right? And believe me, this is not a simple world, a world you can believe in Avengers like that. So Bernoulli distribution, the simplest one. What Bernoulli distribution is saying, and each distribution is you can say referring to one kind of an experiment, right? Every distribution, like it's hundreds of distributions, and we are not learning all of them. Okay, so first distribution, Bernoulli distribution, is related to an yeah, what you call that event or experiment where you have just possibility of getting just two outcomes. Either it is positive, either it's negative, or you can say one or zero. If the outcome of your experiment is binary, right? If it is binary, one or zero, true or false, then it is called the Bernoulli experiment, and the distribution for that probability, it's nothing but the dense it's Bernoulli distribution, right? And as you have guessed it, we have the PMF here, not a PDF, because it is discrete, correct? And what is the probability for the true? And see, this is kind of a you can say how to name it, convention, that by convention we write x equal to 1, the true probability, or the event being equal to 1, or if the event occur, then we call it a positive event, and and to denote that, the probability is denoted by p, right? And that opposite of it, or the complement of that event, is nothing but 1 minus p, right? So if there is a probability that I get head is 0.5, given a coin, if it is zero point 0.5, then what is the probability that I will get tail? It is 1 minus zero point 0.5, right? if coin is bias if coin is bias and the probability of getting head, right, it is zero point 0.7, then what is the probability of getting tail? 1 minus p. Sometimes it is called q also. Q equal to 1 minus p. So p is positive or 1, q is negative or 0, right? Okay, so what is the mean of it? It is p, and all these derivations are there in the content. I don't know if it has any value or something. Okay, so expectation of x equal to p, and variance of x is nothing but pq, right? And if you think like think in something, say what is the expectation, right? We can derive it from first principle also. What is expectation? It's nothing but the value of x multiplied by probability. So 1 multiplied by p, 0 multiplied by q. So what you get? 1 multiplied by p only, right? Like that. And what is the variance? Pq. Okay. So p, or p into 1 minus p also, it is said that. And how to draw the PMF? It's really simple. Let's say I have a Bernoulli distribution, and it is mentioned something like this. Let's try to draw it, because sometimes it is boring to see everything drawn already. So if I say I have distribution Bernoulli 0.3. So what is the meaning of Bernoulli 0.3? I hope I got the spelling correct. Yes. So Bernoulli 0.3. So this 3 is nothing but p, or the probability of my success event. That means what is the probability of x equal to 1.3. So what is the probability x equal to 0.7? Right. So how can I draw the PMF? Anyone? So here it is 0, here I am 1. So at 0 I have zero point 0.3 probability, and at 1 I have zero point 0.7 probability. This is zero point 0.3, this is zero point 0.7. So if I want to generalize it, it is nothing but p, and here it is nothing but 1 minus p. How can I draw the CDF? So first up to 1 I have p probability, Then after that, p plus 1 minus p is nothing but 1. So your CDF will look something like this. So this is p and this is 1. Correct? Any doubt, guys? Koi shak? Wait, this is 1 minus p. Kill me. Oh, okay. We have a problem here. Huh. Okay. The problem and this confusion is not new. Okay. Okay. Let me tell you what was the problem. So what we are saying is by convention, P is nothing but the probability of success event, right? X equal to 1, right? So the P, the value that we are showing here, it's for the success event. So this whole thing will go into bin now, right? So by default, if I say P, it's for X equal to 1, right? So how to now draw it? So for 0, the probability is zero point 0.7, and for 1, the probability is zero point 0.3, like this. Now it's correct. This is P, this is 1 minus P. For 1, I have P, correct? And for CDF, now it will look something like this, zero point 0.7 for 0 to 1, and at 1, I have zero point 0.3 added, right? So zero point 0.7 plus zero point 0.3 is 1. All right, so here it is 1 and here it is 1, 1 minus P or Q, you can say. Sorry for the confusion, but yes, it is looking something like this. Bernoulli 0 0.3 is like this and Bernoulli zero point 0.7 is like this. Okay, let's jump on to next distribution. First was boring itself. So let's combine, like let's have group of them. Right, so binomial distribution is nothing but if you are doing an experiment or an experiment, right? Let's say you are tossing a coin for 10 times, right? Then then or let's take one more example. Actually, I also don't like when someone gives example of coin toss. Let's say again, let's take the coin toss example, but let's say there are like 10 you can say toss, 10 toss, yeah, like 10 toss in, let's say, one of the tournament that Virat Kohli is going to do, right? What is the probability that he will win 5, right? Now what he decided is, let me tell you a story. Virat said, I will say head every time. I will say head every time with for all the 10 matches, right? So what is the probability that 5 times it would be head, and basically 6 times he will win the toss, that means 6 time head. What is the probability that he will win all the toss and decide to bat or ball? It is like I don't know, whatever the Dhoni will suggest he will do. So what is the probability that he will win 4, or even what is the probability that it is 0, right? So how to decide this? So for this problem, this great you can say probability engineer come up with the binomial distribution, right? So what binomial distribution is saying, if I have n such you can say n events or an experiment, and each experiment is Bernoulli. What is Bernoulli? Bernoulli is nothing but it can have either 0 or 1. The outcome of all these events, all the you can say this independent event, and all these events are independent basically, right? Is independent of each other, and it can take just what two value, right? So these all experiments are Bernoulli. So if I am doing Bernoulli experiment for n times, then it is called the then it follows the binomial distribution. And what the binomial distribution is saying, the probability that you will get x equal to k, that means what is the probability that I will get 6 heads, right? If I'm tossing a coin for 10 times, right, Virat is saying head every time, right? So what is the probability that x equal to 6? X, not x equal to 6 particularly, I don't know how to say that. Capital X equal to k. Okay, k is nothing but 6. What is the probability that I will get 6 heads out of 10? So that is defined by this formula. n c k, n choose k, p to the power k, 1 minus p, n minus k. Boring. So what is the probability that I will get 6 sides, right? So for these 10 matches, it is possible that he can get all the 6 heads in the first 6 matches. One head here, one head here, one head here, one head here, like that, right? He can win the 6 toss, or the 6 heads out of 10 can be somewhere, like we can arrange these 6 heads in these 10 places in n choose k, that is nothing but 10 6 6, 10 c 6, right? So there are 10 c6 ways to arrange these 6 heads out of these 10 places, because it is possible that first 6 match he win, last 6, or alternating 1 2 3 4 5 and 7, like that. So there are total these ways. Yeah, so we need to count them all, multiplied by what is the probability of getting head, right? So it is p and 1 minus p, right? So what is the probability of success event? So success event is nothing but getting head. So the probability is 1 by 2 multiplied by k. How many heads I want? 6. What is the probability of tail? Again it is 1 by 2. So this is not every time it would be true. The probability can be 1 by 3 also. Then it would be 1 by 3 and 2 by 3 here. Right? And here it would be 4. But in case like probability similar, it is always 1 by 2 raised to 10. Just to save a time, you can write 1 by 2 raised to 10 directly if the probability is similar, right? So if p and 1 minus p is similar, then what will happen here? Where it is, kulja sim sim. K and k will cancel, you will have direct p to the power n, like this, p to the power n, 1 by 2 raised to 10, right? So this will give you some answer. And if you do for x equal to 0, x equal to 1 2 3 4 5 6 up to 10, then you will get graph something like this. This is not for that, but if probability is 0.5 and there are 40 toss, right? Then there is a highest chance that 20 20 20 hit 20 till. This is the highest chance. Now this is a PMF. So this is the probability. It is nothing but about 11%. Correct? And all 40 heads, there is some probability 0.0001, like that. Correct? Because if you put 40 here, then what will happen? This term would be n minus 0, 1 minus p raised to 0 would be 1, right? Raised to k basically. So zero point 0.5 raised to this. So getting 10 head is, it's having some probability, but very, very much less probability, 0.000 something like that. But it is possible. What I need, I am trying to make a point is it's possible. Okay, so how the CDF is defined? It is nothing but just take the CDF formula, calculate all these PDFs at given point at 0 to k basically. So calculate what is the PDF at 0 plus what is the PDF f 1, 2, 3, 4, 5 up to k. So it will give you the CDF for k. And what is the meaning of CDF at k? X is less than or equal to k, right? So we are just taking the summation over I equal to 0 to k of nci pi 1 minus p ni, like this. So basically we are putting 0 1 2 3 4 up to k. Any doubt? So this is expectation formula n into p, variance formula np q, np 1 minus p, right? And
Uh,
to mug up
Mayur,
all that, I have a cheat sheet.
any easy way to remember these formulas, all the distributions?
uh, if it
Only
is
writing and going.
if it is possible for you, just have this kind of intuition. So if let's say if I forget about this, then you can derive it also, right?
Okay,
If I forgot
intuition.
what is
One
right.
example, if you remember and do means.
Definitely. This coin toss example, that's why they are giving coin toss example. If you remember this coin toss example, and if I remember, like, what is the probability of getting 6 hits? If I don't know binomial distribution, we are solving this kind of a formula, this kind of a problem in probability, but we don't know, we are applying binomial formulation. This is binomial formula. 10c6, 1 by 2 6, 1 by 2 4. So this is nothing but nck p to the power k. This is k, this is k. This is n minus k, q to the power n minus k. Right?
Okay, got it. Thank you.
Okay, so let me go. Even I don't remember this. I am going to mug up basically. Yes, there is no
Yeah,
problem in it, right?
yeah, yeah.
They
It's
are
only
forcing us,
yes,
and
yes.
definitely we are not going to use it.
Right, right.
And okay, let's jump on to next distribution. And by now you must have this idea like why we are understanding this kind of distributions, because this is all the, you can say, pattern that we are observing in this very simple looking events, right? We are trying to formulate it. What is the probability of getting zero heads, that we will lose toss every time, like this.
And there are some properties for binomial distribution, like all the
Uh-huh.
n in, so there are n independent trials. Like the
Uh-huh.
trial should be independent, and each trial has only two possible outcomes,
Huh.
and the probabilities of two outcomes should remain constant.
Correct, correct. Over all the value of n. Yes.
Yeah,
Yes, yes, yes.
that's
Definitely. Okay. And the CDF is looking something like a S curve. Whenever you have this bell kind of a curve, you will mostly get the CDF. Uh, Beautiful looking S like this. S curve. Right. Okay. Let's then jump on to uniform distribution. Right, this is used in our random number generator in numpy, this uniform distribution, right? Because if you are generating a random number between 1 to 6, let's say you are designing the game of ludo, right? Then you don't want, I guess they are doing some kind of a coding that you won't get one if you are at last place. But but basically, if it is completely random, then it should follow this uniform distribution. So what is the meaning of uniform distribution? Given the value of x in a range a to b, we have these two parameter a and b. So this is like from a to b, I am having a uniform distribution, right? Probability, or you can say the density, probability density. And if the density is constant, that means probability is also constant, right? So the probability of any value between a and b, it is nothing but the same, right? It is similar. So if I take, I guess in statistics notes we have at last, let me have that. I hope it is there. Okay, continuous and so we have this two kind of uniform distribution, continuous and discrete, right? So from a to b, if it is continuous, then this height is nothing but 1 divided by b minus a, right? In case of discrete, the height or the probability, in case of discrete, we can directly say it is probability. So the probability of any, you can say, a variable, any value of a random variable is 1 divided by n, and this makes sense, right? If you have six discrete, you can if six discrete value that your variable can take in case of dice, then what is the this thing, what is the probability of getting one or two, any value, right? Up for 6, it is 1 by 6. And what is 6? 6 is nothing but number of values you have from a to b, right? So this for this height is different in case of continuous and in case of discrete for this uniform distribution.
so the
And
y-axis is not the probability, right? It's a PDF, right?
in pdf, just a second.
So that 1 minus 1 by b minus c and 1 by n is a value, right?
In case of PDF, see here, just let me think for a minute. Think for a second. In PDF, we cannot say this is probability. This is density. And in case of PMF, or you can say the discrete random variable. If it is discrete random variable, we have uniform distribution. In uniform distribution, it is probability, right? If there are, let's say, 10 face dice, and the probability of getting any number is similar, then probability of getting any number is nothing but 1 by n only, right? Because you have n such events, n such values that x can take. So 1 by n, 1 by n, 1 by n times will sum up to 1. Yes, so the total probability would be 1. But in case of continuous, you can't say this is probability, it is density. And
Yeah, so it's so 1 by b minus a, like intuitively it's saying like you can take any value between b minus a, that area, right?
this
Is
area
it?
should be 1, right? This area should
Yeah,
be 1.
the probability of picking any point between, so b minus a will be 1, or not in PDF.
Not in PDF, but the probability of choosing any number would be, you can say, similar, right? It is equally likely to choose, if you are taking 1 to 10, equally likely to choose 2. Same probability goes for 3, right? And actually, see why there is a paradox here also. I don't want it to go there. Don't want to go there, but let me explain what that paradox is using this uniform distribution. So let's say I have 1 to 10, and this is a continuous random variable, right? So I at, let's say, around 3, and I have 3.00001, right? Next value up to dx 3.000 something 1, right? It can be infinitely small, right? 3 plus 0.0001. Now, how can you, what probability you will assign to 3, right? So there are, and see, I can have infinite values between 1 to 10, and sum of all should be 1. uh, the sum of all the probability, there is not, probability is not there in the graph. The probability of 1, probability of 1.0001, 1.0002, 2, like this, all this number, if I give, this is probability 1, probability 2, all these probabilities should sum up to 1, right? And there are infinite parts, right? So what would be the probability for any number, any particular number, right? So what would be the probability for this number? It would be nothing but some probability, total probability, that is nothing but 1 divided by infinity. So it's nothing but 0. So this is paradox, that in continuous variable, random variable, the probability of any discrete exact value is 0, right? So if you want to calculate, so like estimate the probability at 3, you need to take the dx step towards right or towards left and calculate the area. That would be the, you can say, the guess or estimation about the probability at that point. But at 3 it is 0. It is kind of a paradox, right? Because you can't say, you need to divide these values in infinite ways, right? Infinite values, then, and it all sum up to 1. So the value for given any distinct point is 1 by infinity is 0. So this is a
So
really
I have
good
a
paradox we
question.
have in PDF.
I have a question, Mayur. If we are taking a continuous variable like delivery of pizza, there will be upper bound, right? Like the
No,
maximum should be
that's not continuous variable then.
the the time taken for delivery or something.
Basically, yes, yes, yes,
That will be
yes.
continuous, right? And the upper bound, there should be an upper bound for a continuous also.
Correct, correct. 0 to
So
24, let's
the
say 0 to 24.
yeah 0 to 24. This 24 number, that the last number bound, if we found a data point, then only it will exist in the PDF or in the distribution.
See, that's say, like, that's the limitation. No, see, we can't have all the possible value between 0 to 24, and you can't say you get the data for 24 exact 24,000. It's not even possible, right? And let's say you get at 24, but you can't get all the data from 0 to 24. And
No,
and what
just
we are
wanted to know
doing
if there
is,
is a data point in the
huh,
distribution, the
huh,
probability should not be zero, but this paradox is like
correct. As
contradicting.
824, we are
That's why
saying
it's a
it's, yes,
paradox.
yes, yes.
Yeah.
That's why it's paradox. Yes. Okay. Let's say, and I will share that link. It was really good article, basically, just for PDF. Long article on Medium, just for PDF. What is the y-axis in PDF? That was, I guess, the title around that. Okay, this is what is this? Okay, in case of continuous, uh, in case of continuous uniform distribution, the CDF will look something like this, right? So we are adding up a small area, this 1 minus b area, then 2 times 1 minus b area, then 3 times like that. So we are adding small area, and it will all sum up to 1 at b, correct? So it's nothing but the CDF. And in case of this thing, discrete random variable, the first would be 1 by n, then 2 by n, then 3 by n, 4 by n, and then n by n. It's nothing but 1. So it will look something like this. Right? CDF will look something like this in case of discrete uniform distribution. Expectation is defined by a by b2, a plus b by 2, a plus b by 2 in both the case. But variance formula, it is b minus a square by 12, and in case of discrete, it is n square minus 1 by 12. I hope I have that formula in this thing. Yes, it's there. Okay. Where were we? Huh. Okay. So we just finished the uniform distribution. Okay, this is not for distribution. This is okay. Now let's have the one, you can say, very good distribution, a very good but interesting distribution, Poisson distribution, right? I don't know why it's. I guess it's after the name of the scientist or mathematician who defined this. You got this. So Poisson distribution have one parameter called lambda, right? And lambda is nothing but the rate of event is occurring, right? So some, let's say some event is occurring at lambda times per given time interval. This time can be in second, minute, hour, day, year, month, anything. Whatever the experiment is, the interval can change, right? If you are calculating for atom, it would be in microsecond, nanosecond. If it is for share market, it would be in second, right? So whatever, as per your this thing, one second. uh, okay, as per your experiment, this time interval can be there, this can be different, but this lambda is nothing but how many time your event is occurring, right? So let's say for first hour, how many visitor you are getting on a website. Second hour, how many visitors you are getting on the website, like that, right? So lambda 10, that is nothing but you are getting average 10 calls per an hour, right? So this is kind of it is, I guess, mean also. Yes, mean lambda, right? So 10 calls per hour, that doesn't mean like in morning I will get all 10 calls, like 8 to 9 I will get 10, 9 to 10 I will get 10. No, it's not like that. It is possible that it is looking something like this: 10 call, then 9, 11, 15, 6, like this, right? So this calls per an hour, if you take the mean, it is nothing but 10, right? So lambda is nothing but the average, or you can say the rate of an event occurring in per unit time, right? Per hour, per second, per day. Okay, and that distribution, that probability distribution, density distribution for this lambda probability distribution for lambda is given by this beautiful equation, lambda power k. So k is nothing but let's say I have this 10 calls per an hour. The average is 10, right? So what is the probability that I will get 15 calls? What is the probability that I will get 15 calls? So if I put k equal to 15, that is 10 to the power. Why it's 10? 10 to the power 15. K is x equal to k, right? There is no problem. 10 to the power 15 divided by why lambda is so much high here? 10. Okay, there is no problem. The formula is correct only. Lambda, that is 10 to the power 15 by 15 factorial e to the power minus lambda, that is 10. So you will get the probability of getting 15 calls in an hour, right? And the distribution looks something like this, right? So lambda equal to 10, so like there are high chance, 11 or 15% chance, 14 15% chance that you will get around what is this? This is 7, this is 13, so you'll get 7 to 13. Most of the call, most of the area is between 7 to 13. So there is a really less chance, 0 point something, 0.0001 chance that you will get 20 calls, because the average is 10, right? So come on, like getting the 20 calls is very rare, right? Maybe on some festival day or something like that. And at lambda equal to 4, so from this intuitively you can understand the distribution, the most of the probability is danced around the lambda, or you can say mean. And as we go further, it decrease, it decrease like slowly, then sharply it will fall, and like this. So for this lambda equal to 4, 5, 6, 7, 8, and from 9 and 10 it directly like goes like this, correct? So this is nothing but the Poisson distribution. CDF is looking like this, as like a curve. Okay. What is this? X1 and X2 are independent in the variable. Poisson distribution. Okay. So let's say we have two random variable and both are Poisson distributed, right? And the rates are lambda 1 and lambda 2. So if you want to, if you take the sum of both, like if you combine both the random variable x1 and x2, right, average call per an hour and average bombarding, if you take the sum of both, then the Poisson distribution rate is lambda 1 plus lambda 2, like this. Okay, then the rate is lambda 1 plus lambda 2, sorry. And the counterpart, or you can say the exact opposite of Poisson distribution, is exponential distribution, right? Or anti-Poisson distribution. I don't know if we can call that, but it is kind of an anti-Poisson distribution. The things will be exactly reversed of this Poisson distribution, right? So in Poisson distribution, we have this lambda, the rate. So here the meaning of lambda is similar, right? But we have one more parameter called beta. So beta is nothing but 1 by lambda. So what is the meaning of that? So let's say I am getting a call, right? I am getting a call. Now the lambda is nothing but calls per an hour, calls per an minute, right? That is 10 calls per an hour or 8 calls per an hour, like that. But the beta is exact reverse of it, or the exponential distribution is exact opposite of Poisson distribution. How? The beta is saying something like this, okay, like what is the probability of the time interval, how the time interval is distributed between two calls. I got one call, I got second call, there would be some time, right? Let's say 5 minutes. Then I get third call, 7 minutes, fourth call, 8 minutes, seventh call, fifth call, 2 minutes. So there is the time is distributed, right, between the calls. So what is the distribution of this time? So it is defined using the exponential distribution, right? And the parameter that for is beta 1 minus lambda. So it is exact opposite of it. The minute per call, right? So how many minutes you are getting, and between two calls, or what is the unit time between two call? It is defined by the exponential distribution, and the formula is quite simple compared to Poisson. Lambda multiplied by e to the minus lambda x, right? So lambda is nothing but see here the lambda is nothing but 1 minus beta, or you can say beta is 1 minus lambda, 1 by lambda, not 1 minus, sorry, 1 divided by lambda, like that, right? So this lambda is don't get confused, this lambda is not representing the time interval between call. It is the calls per minute, calls per unit time. It is same as Poisson distribution, but we are using it here, lambda e to the power minus lambda by x, right? So if you are given that it is 1 minute, beta is 1 minute per call, then you can say or beta is nothing but 10 minute, then what would be the lambda? It would be nothing but 0.1, 1 divided by lambda, zero point 0.1, right? Then put it here. Don't get confused, this lambda is from Poisson distribution. CDF is defined something like this. Expectation of x, or mean value, is beta, or you can say 1 by lambda. and the variance is beta square 1 by lambda square. One thing I just forgot to mention is here the variance is also lambda. I guess there is a typo here. Let me confirm. Yes, for Poisson distribution,
What?
the expectation and variance is lambda. But for exponential, I guess it is beta and beta square, if I'm not wrong.
Did you know why both are equal? Any idea?
Uh, I currently don't have any idea. I guess we can derive it, but intuitively,
Yeah.
I don't know.
So I think intuitively what is Poisson distribution is that the occurring of rare events,
Uh
but
huh.
there will be a lot of number of trails will be large. So
Okay.
there will be a number of trails will be large, but a certain event occurring is the probability of occurring that event will be very 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 less.
Ah.
So I have seen that usually, right, even now in the medicine field, let's say you have developed an injection.
Okay.
Okay, you want to know how many people will suffer bad reaction to it,
Okay.
right? So they use actually no Poisson distribution to find out, like, let's say what is the uh, so let's say what is the probability that out of 2000 individuals have developed an
Mm-hmm.
injection. Let's say that the probability of an individual suffers a bad reaction is a 0.0.001.
Okay.
So I want to determine what is the probability out of 2000 individuals. Let's say I want exactly three, like or more than two, or
Okay.
none, or more than one individual suffer a bad reaction.
Mm-hmm.
So usually occurring a bad reaction, even they are saying it like 0.001. So the probability of occurring an event is very very low,
Okay.
but number of no trails is large,
Ah.
right? So usually in those cases they will go for Poisson distribution.
Hmm. Okay. So
And
everything is
also,
between one sigma range like that, right? Around mu we have more density, but if you go in trail, you will have long trail, but the less probability, right? If my
yeah,
understanding correct.
yeah. So what is variance? I think if the not what do you say, uh, maybe I think that's why mean and variance is equal, because the occurring of events is also very very less, right?
Yes.
So
Yes.
you
Yes. Yes.
may not see too many events occurring.
Correct. Correct. So
So
from for this one sigma range, so sigma square is lambda. So in one root lambda, like we are getting almost like the variance is very less, right? So from mu, if you go like far and far from variance, 1 sigma, 2 sigma, 3 sigma, this trail would be really, really small. Correct?
yeah, yeah.
Correct, correct. Okay, okay. Now I understood. Okay. Why the variance in mean is similar. Okay, great. And this extreme case is here, see lambda equal to 1. Everything like fall around 4, like it is very small. Around 5, it is now
Yeah,
around 0.
yeah.
Correct, correct,
So
correct. Yes, Giriteja, come on. Go on. You're saying
that's it.
something?
That's it. That's it. You can carry on.
Okay, thank you. Thank you very much. Okay, so there is a typo here. It should be lambda here. And for this exponential distribution, the variance is beta square or beta. I need to confirm, but I guess it's beta square only. Yes, otherwise I would have changed it here. Okay, let's take the next distribution then. Okay, there is a, I guess there is a one thing. The one example is given between this thing exponential and Poisson distribution. And yes, see here we have this PDF exponential distribution. It's for continuous random variable. It is 1.5. So this doesn't make sense, right? Probability cannot be 1.5 as we discussed. For lambda equal to 1.5, it is starting at 1.5, right? So this exponential distribution, there are some you can say use also where it is. I guess I should have something like this. This exponential distribution, or next, I guess we have that power law distribution. This is only power law distribution, right? Uh, am I making any mistake? Exponential. Am I confused between? Do we have any other distribution like this? We have this Pareto. Yes, it is also looking like exponential, but it is falling drastically. Okay, so okay. I guess I need to see for applications, but yes, this exponential distribution. Let's take one example of internet traffic and try to see what is how can we relate this Poisson versus exponential distribution, right? So let's take an example, and what we are having is the lambda is 3 per hour, and this is example for internet traffic on your website, particular website, right? And I have taken this from Z statistics video. This are from Z statistics. So this is nothing but lambda equal to 3. That means per hour you are getting 3 unique visitors, not the recurring. If I am going every day there, this is unique visitor, right? So lambda equal to 3, that is 3 per hour. Per hour you are getting 3 unique visitors. So the PMF is looking something like this, right? And it is Poisson distributed, let's say. So if you put lambda equal to 3 and do the math, you will get PMF looking something like this, right? So the chance of getting 2 3 4 and 1 1 2 3 4 is like very much, but getting a 0 or getting 7 8, right, it is very less. If the average is 3, let's say every hour if you are getting 3 unique visitor on an average, then it is very less chance that you will get 6 or 7 or 8, right? And what's the meaning of exponential distribution in this case, right? So this is nothing but what's how many hours then the next arrival, like that. That means see, if I take the inverse, then how can we imagine beta in this case? So what's the meaning of three unique visitor per hour? That means at every 20 minute I'm getting one visitor on an average. On an average every 20 minute I'm getting one visitor. So 21 42 63, like that. 60 third visitor, right? So at every 20 minutes, that's what he's trying to show here. At every 20 minute I am getting visitor, right? So this is the exponential distribution. That is like what is the probability that I got you can say one visitor, or what is the probability of that the time between two visitor is nothing but 2 hours. That the time interval between two visitor is 2 hours. It's very less, right? Because at every 20 minutes I'm getting one visitor, and for 2 hours I'm not getting any visitor, right? The time interval is 2. That means it's very less, right? At 0 it is 3. That means there is always a like high chance, or you can say let's say you get or you get this how to you can say explain this. You get a visitor, then what is the chance that you get next visitor, right? So it is like very much high chance around 0. And if you go further, if you go further at 10 minute, there is a still chance. 20 minute a chance. So this is nothing but the probability of the time interval between two visitor. So if you go to 20 minute, there is some like high value. But if you go to 1.5 hours or 2 hours, the probability density, not the particular probability, this is not probability, this is probability density, right? So if you go to 2 hours, then the probability is very less, right? Why? Because the interval between two like two visitor is like for getting a 2 hour is very less, because every 20 minute you are expecting a new unique visitor, right? So this exponential distribution is saying something like this. Okay, let's okay, this is nothing but the CDF, and there is nothing to like worry more about it. And okay, see, it's simple to understand, like after PDF, that what is the chance if lambda equal to 3? That means the 3 unique visitor per hour. So what is the probability that I get visitors 10 or less? Around 100%, right? And what is the chance that I will get around 6 or less, right? So all my x 96% chance that you will get 6 or less, right, if average is 3. So the CDF is nothing but the cumulative, you can say, density function. And similar goes for exponential distribution. What is the chance that I will get visitor in 2 hours? At every 2 hours, 100% chance, because the average is 20 minutes. Correct?
Mayur, so
Yes.
the PDF cannot be continuous and the exponent, sorry, the Poisson distribution should be always discrete and the exponential should be continuous. It cannot go
Uh,
other way, right?
I guess so. I want to make a
Because we can,
comment. Huh, because we can't count, no?
yeah,
Yes.
yeah. In the
Per
exponential,
hour.
we are counting the time per unit time, and here per unit.
Yes, 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 yes. I guess that makes sense basically. Correct.
Yeah, so basically, exponential distribution is nothing but the time interval between events in a process, right?
Yes, yes.
So if two events are occurring in Poisson distributions, you want to know the time interval between those.
Correct, correct.
If you want to know
And
that, you
uh,
use exponential.
and time like belongs to R, right? Real value. It's real value, so it is continuous. Okay. What is this? Memory-less distribution. Yes, there is this point I miss. So what it is saying is the probability of occurring at x given s plus t, that this time interval s plus t, given we have the x is greater than s, it is probability of x greater than t. So what it is saying is that let's say we have waited for s time, right? So s can be, let's say we have waited for 5 minutes, right? Now the probability, so this is conditional probability, right? So this is the base case, or this has already occurred, that x is greater than s, right? So we have waited for 30 minutes, that means 30 minutes is gone. Now what is the probability that x greater than s plus t? That means what is the probability that event occurred in 40 minutes, right? 30 minutes gone, 30 minutes we have waited, it is equal to probability that event will occur in 10 minutes. So it has nothing to do with this thing, this 30 minute, right? So it's called memory list distribution. And
So
huh,
basically, it says when a random variable occurs, then it is reset. Like you can like go again with the same value. Like 40, like here 30 plus 10, 40. So we can
huh,
measure the 10 individually. So it
correct.
resets after occurrence of a experiment
Yes, yes,
at the
yes,
same
yes.
rate.
Kind of a thing. Yes, yes, yes. We have, see, this 30 minute is already gone, right? So the 30 and if event is occurring in 40 minutes, what's that meaning? What is the meaning of that? That means there is one event, then after 40 minutes there is second event, right? Now you have waited for 30 minutes. So what is the meaning of that? For 30 minutes there is no event. Now 10 minutes is there. So what is now? Now what they are saying is there is no like this thing. Then what is the probability that it will occur in 10 minutes? So it is same as the event occur in 40 minutes. Let me draw this.
Can we say it is independent of like
Independent, kind of independent. Yes. So let's say first you are here, right? And now I ask that now you are here, right? You don't know like if event is occur or not, right? Now I say what is the probability that or likelihood that you will get a next call in 10 minutes, right? So this is the point two, 1 to 2. You will say it from this thing, pdf cdf, or using the formula or anything, right? So there is some value here. So now what they are saying is now this is 30, this total is 40. Now let's assume you are here and I'm asking you what is the probability that you will get the second call, the call in 40 minutes. So you will say something like this. There would be some formula, there would be some value. So this is x1, this is x2. This want to be similar, but now I am saying is you have waited for 30 minutes, so this time is gone, right? So there is no call, phone call here, right? So the probability that you will get a phone call in 40 minutes given you have waited for 30 minutes is similar as the you will get a phone call in 10 minutes, right? So this is the your, you can say, memoryless property, right? There is no like dependence on waiting period. right? So this will decrease one by one. The probability of getting phone call in 10, 9, 7, 8, like that.
Yeah, so the probability of
Ah,
10 is equal to probability of 40.
yes. Given that there is no phone call
May-
between these
Yeah.
30 minutes. Correct. So that's nothing but the memoryless property of this exponential distribution. In Wikipedia, I guess proof is given. I haven't seen. Oh, this mu and sigma square is out of normal distribution.
So what is the exact sense of it? Like, what is the use of it? We understand. I think the concept is clear, but
Huh.
in real world, what is the use of it? I don't have the memoryless concept.
Correct, correct. I even try to find that. I remember it clearly, but let's try it again. I don't remember like, and even I can't think of a event also. Like, what's the use of this memoryless distribution? Correct. Yeah, that can be proved, but I don't know what is the use. So better to have it answer. What is the memoryless or memory independent? Memoryless exponential distribution. Uh, they are not answering this. There is no bearing on its future behavior, regardless of how much time it has elapsed. I don't know. And I can think of an example like we in which kind of a Poisson distribution you will apply this, right? Because if you can think of a Poisson distribution or Poisson event, then we can think of like if this behavior is like useful of this exponential distribution. But that's a good question. I will try to find it if I can find some
Sure, sure.
example.
We
Sure.
can do it in offline. We can
Yes, yes,
carry on.
sure.
So can we say like if you order a pizza and we are waiting for it and 30 minutes are passed and the pizza is not arrived, so the probability will be same. It will not increase because we have waited 30 minutes. It will not increase. It will remain the same. It will like it
It would
was
be same as like you will get in
yeah
10 minutes.
10 minutes or yeah exactly.
You'll get in 10 minutes, and it would be higher, right? You will get in 10 minutes. Probability of getting pizza
Yeah,
in
right.
10 minutes is
The
higher, no?
exponential.
It's higher. Yes, yes, yes. It is higher or less? I don't know. It would be higher. Yes, yes. We are okay at 0. It's higher. No, it's is equal to lambda. Then it fall. Correct. So see, we can. So I don't know if we can interpret it like this. Correct me if I'm wrong. So more and more, like we are waiting, the chance of getting that event done is increasing, right? You don't get a bomb like since like 30 minutes, and the average is like 30 minutes only, or you can say at every 40 minutes you are getting a bomb, like the bomb is you are getting a hit, right? So like still 30 till like 30 minutes it was like there is no hit. Now what is happening is as the time is decreasing on x-axis 5 4 3 2 1, the chance of getting a hit is increasing, right? Because if you think the chance of getting a hit is increasing because the 30 minutes is already gone, and you are expecting a bomb at every 40 minutes, right? So as the time increasing, the wait time increasing, this s increasing, the t decreasing, and as the t decreases, the chance increases. I don't know if we can interpret that, but yes, that's a good Google search exercise before sleep today. Okay, how many are there now? I also got kind of a board now. Three, only last three. Cool. And these three are now very, you can say, we are used to it. Normal due to machine learning, log normal, both are kind of a siblings, and Pareto due to this exams. or specifically mid 3. Okay. So normal or Gaussian distribution is nothing but the most natural, you can say, distribution that is observed in nature, right? That's why it's called most natural distribution. Why? Because in nature, so many phenomena or so many occurrence or so many things are following this kind of a distribution, normal or you can say Gaussian distribution, right? And the parameter that we are giving is also very standard. Mu, that is nothing but mean. Sigma square is nothing but the variance, right? And the normal distribution or the Gaussian distribution is nothing but having a bell curve, right? And it's around, and all the probability is around, you can say, danced around mu, right? So around the mean value there is a high chance of getting this thing. And as you go, like, move further and further, it depends on the sigma or variance. So how, what is the value of this tail, or how it is distributed, or how it is concentrated around mean, is defined by variance. So lower the variance it is, higher it would be concentrated around mean, right? So for the same mean mu equal to 0, we have sigma square equal to 0.215, right? So if sigma square is zero point 0.2, this blue curve, all my values are concentrated around mean, right, heavily. So if I increase sigma by 1, sigma square by zero point 0.8, and sigma square equal to 1, now it is looking something like this. Again, a bell curve, symmetric about this axis passing through mean, parallel to y, but it is like varying much, right? So there are like high, this density is varying much. So if I take sigma is equal to 5, it is varying like at everywhere, scattered, right? The values are scattered. Okay, that's the, you can say, this thing, nor how the normal distribution of probability density is, and this is the formula. And this formula is nothing but for this thing. So if you put value of x for from this -5 to 5, you will get this kind of a graph, right? 1 by sigma 1 to 2 pi, don't, like, no need to read it. And the fx is nothing but just taking a integration of fpdf. We don't have a particular formula of it. Okay, mean is mu, variance is sigma square, that's what we are giving in the parameter. And it is followed by very very, like, so many natural phenomena, like height of a person, or every biological parameter, or you can say characteristic of almost all creature on earth follow the normal distribution, right? So if you take even elephant, the weight distribution of all elephants would be Gaussian. Okay, and in machine learning also we are assuming in so many things. In linear regression also we are assuming that x is that data is normally distributed around the mean value, and like that we have so many assumptions in machine learning. Okay, okay, what's this 68, 95, 99.7 rule is? So if you take one sigma range, so sigma square is given, right? Sigma square is, let's say, 100. So sigma is 10 and mu is, let's say, 0, right? So from one sigma to one sigma in this side and one sigma this side. So one sigma is range is nothing but mu plus sigma and mu minus sigma. If you go like that, so if mu is 0, sigma is 10, then it is nothing but minus 10 to 10. The observations are nothing but you will observe is 68%. So that is 68% of point are having the value between mu minus sigma to mu plus sigma, right? If you go to one more range, 2 sigma range, mu plus 2 sigma, mu minus 2 sigma, right? Then 95% points are distributed between this range. If you go 3 sigma, then 99.7%, right? So above 99%, only 0.3% points are having a value greater than 3 sigma, mu plus 3 sigma, and less than mu minus 3 sigma, like that. Okay. Log normal distribution is, see, it is kind of uh, you can say improvement in a normal distribution. because every time you want to see kind of a perfect or symmetric distribution in case of this normal distribution. So sometimes what will happen is the like on one of the side or right hand side, as the value of x increasing, the chances of probability will decrease slowly or fast, depend on the value of this sigma, or you can say variance, right? So it is nothing but the probability of like not probability, characteristic of log also, right? It increases but very slowly, right? Simply, so if you have a thick tail kind of a thing, that you have like high chances around 2.5 also, 2 also, but most of them are you can say danced around mu, then you will use the log normal. And how you define the log normal distribution, and this is nothing but the natural logarithm, and it's always natural logarithm ln, right? So if your data, if you take the log of your all the observation, and if it is following the normal distribution, then it is log it, then your data is called as log normal distribution, and it will look something like this. So for all the data, if you take the log, then it is perfectly normally distributed. That's why it's called log normal distribution. Correct? No, so here I have given the intuition more likely to happen in short interval, then the probability decrease slowly over the time based on the variance. Then we are using this log normal distribution. The good example is users dwell time on online article or length of chess game, like that. So there are see in most of the like when the article is posted or something, you will see like most of the comments are between let's say 0 and 1 month, right? After that there would be a comment, but if you had like 1,000 or 2,000 comment in 1 month, then next 1,000 comment would be in 2 or 3 months, like that. Correct. So over the time it decreases. It's never zero, but it decreases slowly or fast based on value of sigma. Right. So here mu is zero for all of this. Only sigma is changing. Variance is changing. Correct. Last but not least, Pareto distribution. Then I will come into this chart. Let me have some water, and this is the last one. Then we will close this session. It's 11:30 already. Okay. Pareto is also one of the you can say infinite distribution. Okay, so Pareto is something like this, that the all the value of x, or you can say your random variable is highest around your expected value, or you can say mu xm is one of the parameter, that is nothing but the scale parameter, or alpha is the sap parameter, how fast it will fall, right? It is defined by the alpha, like that, right? So the Pareto distribution is very much useful if you have a very, you can say, imbalance situation, right? If it is not balanced, let's say this income distribution, right? So it is log normal also, sometimes it is defined as log normal up to like 95% or 90% of the population. But if you talk about the top 5% population, right, top 5 you can say top 5 earning person in the on the earth, then their wealth is distributed Pareto, right? If paper is so hard, then the mark distribution would be Pareto, right? So mostly most of the person would get the average mark. Then there would be some exception that they will have higher mark, like that. Or if you take the income thing, then there would be like top 5 or 6 people. Or if you talk about like just 1% of a people would be holding like so much of a wealth, right? But the number is very very less compared to some billions of a people. right? So if you take this one, this is also good example, oil reserves, right? So if you take the oil reserves, right, and the amount of oil they are holding, right? So if I take 5, that means 5, let's say 5 million liter, right? So there would be very very less, or like 10 or 12 just oil fields that would be that much of large, right? So I will have so many fields that have the average value, or around this value, 1 2, like this average value, basically whatever the parameter I took, right? So it's called the Pareto distribution or power law distribution. And the formula, I guess, we didn't discuss. The formula is very very, you can say, ugly looking like thing, but the intuition is this, right? And how to check if it is following Pareto distribution or not? Just take the log of x and log of this thing, probability density function. And if it comes to linear, that means it is following this thing, Pareto distribution or power law distribution, right? Okay, now let's come on to the last topic. That means how to find the RV. What for what you call this distribution, this random variable x is following, right? So if it is following log normal distribution, then what is the taste of it? How to taste this thing? How to perform, like how to find out it is following log normal? Just take, let's say you have x1 x2 x3 up to xn. Just take the log of it, then you will get y. So y1 is log of x1, log of x2, log of x3, like that, y1 y2 y3. So this y would be following the normal distribution, right? So y is nothing but natural logarithm of all this value, and it would be following the normal distribution. That means your x is basically following the log normal distribution. If we talk about the Pareto distribution, and there are two ways, that log log graph, this log log graph, right? And there is one more. Okay, there was a one QQ plot we will discuss tomorrow. There is one more, you can say, hack that you can apply on a Pareto. You can apply the box Cox transformation, and that's what we would be doing if we have Pareto, because normal distribution is very much easy to handle, and most of the algorithm is also designed with keeping in mind that y follows the normal distribution. So how can we convert Pareto into normal? We will apply the box Cox transformation. So the box Cox transformation, if you apply, you will get the y, right? And y follows the normal distribution. So what is the formula of y? So yi, that means y1 is nothing but x1 to the power lambda minus 1 divided by lambda. And what lambda is? Lambda we will get, and there is a very high, you can say, high level mathematics applied to convert the Pareto into normal, and getting this parameter, basically lambda, right? And this lambda, if you put lambda in this equation, x to the power lambda minus 1 by lambda, or ln lambda, if lambda is equal to 0, what is this? This should be ln of xi, I believe. There is also one problem here. One second. Do I have a formula here that for the box Cox? It should be ln of x, right? I remember it. Ln of lambda doesn't make any sense. Lambda equal to 0 for lambda equal to 0, right? So just take a natural logarithm up, or if lambda is not equal to 0, just take this thing. So how to calculate lambda? It is beyond the scope of this, and even I don't know. Correct? Any doubt, guys, or anything, any suggestion, anything?
If we apply box cause on log uh, one, did we get? Can we get normal?
See, if we applied log normal distribution box cos, your lambda would be 0, basically, right?
Okay.
And
Yeah.
if you think the Pareto in log, both are looking some way similar, right? So what internally they are trying to do is, how they are comparing, like how this Pareto distribution is skewed like this, compared to log distribution, right? It is also skewed if you take a high value of this sigma. If you take higher and higher value of sigma, then it will start looking like this thing, this Pareto, right? Because it is the tail is increasing, right? And if lambda is equal to 0, what we are doing is we are applying a natural log on x. That means x was following log normal distribution. So after applying box cos, if we get lambda equal to 0, that means it is log normally distributed. Anything else,
Yeah, got it.
guys? Yes, yes. Okay, guys. So let me stop the recording. If nothing is there, tomorrow we would be studying that statistics, and I hope like tomorrow everything is completed, the theory part. Then we can start the numericals.